In this video, we'll be looking into the decomposition product when a metal hydroxide would be heated. So let's start with seeing the general trend according to which a metal hydroxide decomposes. So a metal hydroxide when heated decomposes into metal oxide and gives H2O. Now there is a proposed mechanism by which this particular trend of the decomposition of metal hydroxide is followed. We have the compound of metal hydroxide here. We see that we have two bonds here. Now different ions will be formed when these different bonds will be broken. For example, if this bond is broken, then we will have the ions M plus and OH minus, and if this bond is broken, then we have the ions MO minus and H plus. Now these two ions can combine to give metal oxide, and these two ions can combine to give H2O, and this is what we see in the decomposition product of any metal hydroxide in general. Now we have a fact here that these ions, that is Be2 plus Ag plus Hg2 plus Hg2 plus, they have a very high polarizing power, and this also we have learned in the previous videos. Now we know that hydroxide, when we look into hydroxide, then we are dealing with a polyatomic anion, and also we have learned that in case of polyatomic anion, the polarizing power and thermal stability are inversely related. So since these ions have a very high polarizing power, so the hydroxide that would be formed with the help of these cations will be very unstable. That means they will have a lower decomposition temperature, and so these hydroxide basically decomposes at room temperature. Now another fact here, that hydroxide of bismuth and antimony converts into oxycations. Oxycations mean basically the cations which contain oxygen as well. For example, we have BiO plus, this is oxycation. So when BiOH whole thrice decomposes is heated, then it gives off H2O, one molecule of H2O, and forms BiO dot OH. Now if we carry further reaction and we react it with HX, then this X minus will replace OH and form the compound BiO plus and X minus. Similar reaction would be for Sb. Now that we have seen the decomposition product of two different kinds of compounds, one containing CO3 minus, that is carbonates, in the previous video, and one containing hydroxide in this video. So let us look into the decomposition product of a compound which contains these two ions at the same time. So the first compound here is CuCO3 dot CuH whole twice, which is also called malachite and basic copper plus 2 carbonate. So the decomposition product would be the addition, simply the addition of the individual decomposition product of CuCO3 and CuOH whole twice. So the decomposition product of CuCO3 on heating would be CuO and CO2, and that from CuH whole twice would be CuO and H2O. So the final decomposition product would be CuO, which would be common, and CO2 and H2O. Now we have learned in an earlier video that when CuO is heated, we get Cu2O. In CuO, the oxidation state of copper is +2, and in Cu2O, the oxidation state of copper is +1, and it gives off O2 as well. Next we have PbCO3 whole twice dot PbOH2. Now this is also called white lead, and when this would be heated, we would get the product as PbO, CO2 and H2O. Quite obviously PbO would come from both PbCO3 whole twice and PbOH whole twice as well, whereas CO2 would come from PbCO3 whole twice and H2O would come from PbOH whole twice. Now an interesting fact here, that when white lead and lithophone, which are both component of paint, when it reacts with atmospheric sulfur, we get black stains of PBS, and the stains, that the black stains is formed according to this reaction. We have white lead, which is the component of paint, and it comes in contact with atmospheric sulfur and it gives PBS, which looks as a black stain to us on any wall that is painted. So this was it for the decomposition product of hydroxides. We have also looked into the compound in which both carbonates and hydroxides are present, and we have looked the approach how we would be finding the decomposition product of these compounds. So in next video we'll look into the heating effect on bicarbonates, oxalates, acetates, and formates.